So we talked about translations and reflections. The next topic is stretching and shrinking. All right, so the graph of y equals a times f of x is a stretching or shrinking of the graph of f of x by a factor of a. If a is bigger than 1, then it is stretching. If a is smaller than 1 but bigger than 0, then it is called shrinking. And the reason we only start from 0 and we don't have any negative values is because if a were negative, the negative sign would be a reflection. So the negative sign wouldn't actually contribute to the stretching or shrinking. It would actually just flip the graph over. Okay, so let's look at an example. Let's graph the equation y equals 2x squared. All right. This is a square function, so first you want to identify the basic type of function it is. This is a square function. And so the basic member of the square family is this function, f of x equals x squared. We are wanting to graph y equals 2x squared. So what's different here? The difference is this factor of 2 being multiplied to the x squared. And because this is bigger than 1, we call this a stretching of the graph of x squared. Unfortunately, the only way to really determine the stretching or shrinking of a graph, there's no shortcut way of dealing with that. You just have to plot points. That's the only way to determine how it changes the graph, is by plotting points. And so let's go ahead and do that. In fact, what I'd like to do is do a side-by-side comparison of the original graph, f of x equals x squared, with the graph of y equals 2x squared, so you can see what that stretching actually does to the graph. So the graph the graph f of x equals x squared, we'll graph that by plotting a handful of points. So I'm going to choose some values for x. So I might choose x equals 0, in which case I would get y is also equal to 0. Right? So if you were to plug in 0 for x right here and into this equation, you'll get y is equal to 0. You could also choose x equals 1. And if you plug in 1 for x, you get 1 squared, and so you get y is equal to 1. You could select x equal to 2, plug that into the equation, and you get 2 squared, which gives us 4. So we get y is equal to 4. Also, you should choose some negative values for x, so we choose negative 1 and negative 2. And when you plug those in, negative 1 squared gives you positive 1, and negative 2 squared gives you positive 4. So if we plot those points on the Cartesian coordinate system, it looks like this. Right? We get this parabola shape, which hopefully you were expecting because you're supposed to have this basic shape memorized anyways. So for x squared, the graph comes out as a parabola, but here's specifically what that parabola looks like. We connect the points according to that pattern, and we get this graph. Let's do the same values of x for the other equation, y equals 2x squared. If we do that, we get the following solutions to that equation. If you choose 0 for x and you plug in 0 here for x, you get 0 squared, which is 0. 0 times 2 is still 0, and so we get 0 for y. If you plug in 1 for x, you get 1 squared, which is 1. 1 times 2 gives me 2, and so I get 2 for y. If you plug in 2 for x, you get 2 squared, which is 4. 4 times 2 gives you 8, and so you get 8 for y. And if you select negative 1 for x, you get negative 1 squared, which is positive 1. 1 times 2, again, gives us 2. And similarly, we get that result for a negative 2, we get y equals 8. If you plot those points on the same Cartesian coordinate system, just for comparison purposes, you get something that looks like this. Now, my Cartesian coordinate system only went up to y equals 5, so I'm really cheating here by going off of the grid. And that's really not a good idea, so please don't do as I do. So do as I say, not as I do. But it should look something similar to this. And so you can see the effect of stretching on this graph. When we connect the points, we get this graph. And this is what stretching looks like. It's been stretched out in the vertical direction. All right, so that's stretching. And again, the only way to determine stretching is by plotting points. There's nothing else you can do for that. Okay, so we've talked about translations, reflections, and stretching and shrinking. And we've looked at each of those in isolation, so individually. But what if you have more than one type of transformation occurring within the same problem? How do you handle that? It turns out the order does make a difference. So if you do a translation first and then you reflect, you get a different graph than if you reflect first and then do a translation. The graph comes out different depending on the order you apply the transformations in. So we want to make sure we do this in the proper order. The textbook suggests a different order than I'm going to suggest. So the textbook has a different method for this, which is valid, but I have a different technique that I like to use. All right, so here's how I would suggest doing these transformations. If you have more than one to deal with, the first thing I would do are the reflections. Specifically, since we're only doing reflections about the x-axis, I would do that one first. If there's a reflection about the x-axis, apply that to the graph first, and then apply any translations that are occurring to the graph. So the second thing is apply the translations, shifting it up or down, left or right. And then the last thing you do is stretching or shrinking. And again, you account for that by plotting points. So whether there is only one type of transformation or several, always make sure to plot points at the end. So even if there was no stretching or shrinking, we're still going to plot a few points. All right, so let's look at an example. We'll take y equals -2 times absolute value of x plus 1, and then to that we're going to add 5. So we want to graph this equation. This is an absolute value equation, so first identify what type of equation you're dealing with. Because it's an absolute value equation, we'll start with the basic absolute value function, which is f of x equals the absolute value of x. And we start with this one because we have this graph memorized. We know what this graph looks like. It is the V shape. Right? And remember, this V shape has the point 0, 0, so we want to keep track of that also. So that's the basic absolute value function, but the equation we're trying to graph is y equals -2 times the absolute value of x plus 1 plus 5. And so there's quite a few differences between the equation we're trying to graph and this basic function. And each one of those differences will have a certain effect on the graph. So let's identify those differences. So I'm going to draw arrows pointing to everything that's different about this new equation. And so here are all the differences. We have a negative sign there. We have a 2 in front of the absolute value. We have a plus 1 directly on the x variable. And we have a plus 5 tacked on to the end of the function. Each one of these differences will have a predictable, we know it's different. What do these differences mean? Well, the negative sign is going to cause the graph to get flipped over. That's a reflection. The 2 is going to stretch the graph by a factor of 2. The plus 1 directly on the x variable will shift the graph to the left by 1. And the plus 5 tacked on to the end of the absolute value will shift the graph up 5. All right, so we need to apply all those changes to our basic graph, our basic V shape, but we have to apply them in a careful order so that we make sure we get the graph correct. The first thing we will do is we will flip the graph over. So that is the first type of, that's the first transformation that we want to apply. Flip it over first and just do that. All right, so when we flip it over, we get a V shape, but it's upside down. We still have this point that's at 0, 0, so keep track of that point. So even after you flip it over, that point there still stays at 0, 0, and from there it's a V shape going down. The next type of transformation to apply are the translations, which are shifting it to the left 1 and up 5. And so we're gonna do that over here. So I'm jumping back across to the left-hand side of the screen, and we'll keep the change we've already made, which is flipping it over. So we'll keep this change and apply to that change, shifting the graph left 1 and up 5. And when you do that, the graph comes out looking like this, right? Something like this. So that point that was at 0, 0 gets moved to the left 1 and up 5. And so now that point's up here. The rest of the V shape tags along with that point. And so we have this upside down V shape, which now emanates from -1, 5 rather than 0, 0. The last thing we have to account for is the stretching or shrinking. In this case, it's stretching, so we'll do that last. And the way you account for that is by plotting points. And so I'm going to make a chart here, and I'm going to plot a couple of points. And the way I do that is choosing a couple of values of x. I don't really need that many because the V shape really has just 2 straight lines. And to get a straight line going, you just need 2 points lining up along that straight line. We already have one here, which is negative 1 comma 5. We already have that point. So we just need another point to the right to get that straight line going in the right direction. And we need another point to the left to get that straight line going in the right direction. So to get a point to the right, I chose x equals 0. So that's the choice I made for x. That's to the right of this point here at negative 1 comma 5. You plug in 0 for x. And let's go through this verbally. I didn't write it down, but we can walk through this. If you plug in 0 here for x, the first thing you do is you add 1 to that. 0 plus 1 is 1. The absolute value of 1 is 1. 1 times negative 2 is negative 2. And then negative 2 plus 5 gives me 3. So I get y is equal to 3. And so I plot that point here, 0 comma 3. To the left, I will choose x equals negative 2. So here I've selected negative 2 for x. Let's go through the same process. We'll plug in negative 2 for x. Negative 2 plus 1 is negative 1. The absolute value of negative 1 is positive 1. 1 times negative 2 is negative 2. Negative 2 plus 5 also gives me 3. And so we get negative 2 comma 3. I plot that point. Right? And now I can finish my graph, and I have a pretty nice looking graph. It's pretty accurate. We have, we have the shape of the graph correct. We have it in the right spot, and we have it going off in the right direction. So there is the graph of the equation. Y equals negative 2 times absolute value of x plus 1 plus 5. The other thing you might be asked to do with this problem is find the domain and range. So again, the domain is how far to the left the graph goes, how far to the right it goes. And for this graph, it goes forever to the left, forever to the right. So you get negative infinity to infinity. The range is how far down and up the graph goes. It goes down forever, and it goes up as high as positive 5. Right? That's the highest y coordinate that we get. And so the range is negative infinity to 5. An even function is a function f of x with the following property. F of negative x equals f of x. Even functions are symmetric to the y-axis. An odd function is any function f of x with the following property. F of negative x equals negative f of x. Odd functions are symmetric to the origin. So you want to remember those symmetries. So at this point, you're just going to memorize them. Later on, we will try to use them for graphing purposes. But for now, I just want to introduce the idea. Notice that for both definitions, the initial left-hand side is f of negative x. So in both cases, the interest is in what f of negative x is going to equal. If it just equals f of x, meaning if f of negative x equals the original function you began with, it's an even function. If, however, f of negative x ends up equaling the negative of the original function you began with, it's an odd function. If it doesn't equal either of those two things, then it is neither even nor odd. So functions don't have to be one or the other. They could be neither of these. The characteristic of being symmetric to the y-axis looks like this. So here we have the absolute value of x function. Right? So this is the basic V shape for the absolute value of x. And this is what symmetry to the y-axis looks like. Notice that for every point on the right-hand side of the y-axis, there is a mirror image point on the left-hand side of the y-axis. So for every point that you have on the right-hand side, there is an exact mirror image point on the opposite side of the y-axis, exactly the same distance away on the other side. That's what it means for a graph to be symmetric to the y-axis. For symmetry to the origin, what we have here is a graph which is very similar to the cube graph, x cubed, but I did alter the points a little bit to make it fit in my grid that I have here. But the symmetry is the same as what you have for x to the third power. And what makes a graph symmetric to the origin is that for every point on one side of the origin, 0, 0, there is a mirror image point on the exact opposite side, the same distance away of the origin, 0, 0. So notice that also happens with the point 1, 1. On the exact opposite side of the origin, we have the point -1, -1. It's exactly the same distance away on the exact opposite side of the origin, and that's what makes it symmetric to the origin. On the homework, you'll be asked to determine if a function is even, odd, or neither, and then upon determining that, they will ask you if, when I say they, I mean the textbook or Math Excel, will ask you if the function is symmetric, if it has any symmetry, if it's symmetric to the y-axis or the origin. So the first thing is to determine if the function is even or odd. The way you determine if a function is even or odd is you look for f of negative x. So if you take that function f of x and you find f of negative x instead, so what we're going to do is everywhere we have an x, we're going to replace it with negative x. On the right-hand side, you will get negative x to the third power minus 5 times negative x plus 1. Simplifying that, the negative sign passes through that exponent of 3, and so ultimately that first term will just be a negative x to the third power. For the second term, we have negative 5 times negative x, which becomes positive 5x, and the last term stays the same. It stays plus 1. And so this is what we want to analyze. The first thing we'll look to see is if this is the same as the original function. If this comes out exactly the same as the function we began with, which is x to the third power minus 5x plus 1, then we have an even function. But you'll notice right away that there are some differences here. The first term in this case is negative, whereas in the original function it was positive. So is this the same as f of x? The answer is no. It is not the same as the original function, and so therefore this is not an even function. To determine if it's an odd function, you want to determine if what we got here is the negative of the original function that we started with. So the negative of the original function, we can do a quick calculation to see what that looks like. So down here, what I'm going to do is take the original function that we started with, and then I'm going to multiply a negative sign to both sides. So if I multiply a negative to the left-hand side, I'll do the same thing to the right-hand side, and I'll end up with negative f of x equals, distributing the negative, we get negative x to the third power plus 5x minus 1. And so this seems promising. The negative x to the third power matches up to this negative x to the third power. The plus 5x matches up to this plus 5x. But the difference here is that we have a minus 1, whereas in our original calculation there was a plus 1. So these are not exactly the same either. Even though it gets pretty close, it's not exactly the same. And so this does not equal the negative of the original function either. And so our conclusion here is that this function is neither. It is not even and it is not odd. And so there's no symmetry to be determined. All right, let's look at another example. Is this function even, odd, or neither? So the function we're given here is f of x equals 1 plus 1 over x squared. So to determine if this is even, odd, or neither, the test for determining that is to take that function and replace x with negative x so we can see what happens. What does it do with that negative sign, right? We're trying to see how it behaves. So if you do that, you get f of negative x is equal to 1 plus 1 over negative x squared. But when you square a negative, the answer always comes out positive. And so what we're going to end up with is 1 plus 1 over positive x squared. Right? And so we ask ourselves, just like we did in the last example, did this come out the same as the original function? Does this result equal the original function I have, which is f of x? Right? And the answer in this case is yes. It came out exactly the same as the function we started with. It came out exactly the same as the original function I started with, 1 plus 1 over x squared. And so we can stop here. We've discovered what this function is. It's even. So we don't have to test to see if it's also odd, because most, almost all functions, and I say almost because there's actually one function that can be both. But besides that, it's either one or the other. Either it's even or it's odd, or it's neither one. So in this case, it's even. So we can stop here. Right? This function is even because when I plugged negative x in for x and simplified, the result came out exactly the same as the function I began with, the original function f of x. And so it's even. And that means that this graph does have a symmetry. This graph will be symmetric to the y-axis. Let's do one more example. Is this function even, odd, or neither? We have the function f of x equals x to the fourth power plus 1 over x to the third power minus x. If we want to know if this function is even or odd, the test for determining that is to find f of negative x. So we're going to take this function, and everywhere there's an x, we're going to replace it with negative x. And so this is what that will look like. We'll get negative x to the fourth power plus 1 divided by negative x to the third power minus negative x. So everywhere there's an x, I put a negative x there. And then I simplify that. The negative x to the fourth power, whenever you take something to the fourth power, it comes out positive. So I get positive x to the fourth power when I simplify, plus 1. And so the numerator reverts back to what it was originally. So even when I plug in a negative x there, once I simplify that, it goes back to its original form. The denominator behaves differently. So in the denominator we have negative x to the third power. Well, that answer comes out negative. So we get negative x to the third power. And then minus negative x becomes positive x, plus x. Right? And so we ask ourselves the same two questions we asked previously. The first question is, did this come out exactly the same as the original function I started with? And the answer here is no, it did not. The denominator is different than the original function, and so this is not an even function. By plugging in negative x for x, we alter it. It doesn't revert back to its original form completely, and so the answer here is no, it's not an even function. So now we have to move on to determining if this is an odd function. So we ask ourselves, did this come out as the negative of the original function we started with? And this is a little bit of a tricky question here. So what does the negative of the original function look like? Well, let's do a quick calculation and find out. I'm going to start with the original function here. And what I'm going to do is to both sides of this function, I'm going to multiply by a negative 1. I'm just going to distribute a negative to both sides. And so what we end up getting is something that looks like this. We have a negative f of x on the left-hand side, which is what I'm interested in finding out. I want to know what that's equal to. On the right-hand side, we get the negative of that fraction. We get the negative of x to the fourth power plus 1 over x to the third power minus x. And we can decide what we want to do with that negative sign. We can either apply it to the numerator or we can apply it to the denominator. So we can do something with that. And we don't want to apply it to the numerator because the thing we're trying to compare it to, the numerators already match up, right? X to the fourth power plus 1 in this numerator, x to the fourth power plus 1 in this numerator. That's already a match. So the only thing that's different is the denominator. So let's go ahead and distribute this negative sign into the denominator to see if it changes it in such a way that it matches up to the thing we're trying to match it up to. So let's see what happens when we do that. So what we end up getting, sorry, it's hard to see. Let me jump down here. What we end up getting when you distribute the negative to the denominator is you get negative x to the third power plus x in the denominator. The numerator stays x to the fourth power plus 1, and we see that this actually exactly matches f of negative x. So these are a match now, which means the answer to this question is yes. This does come out exactly equal to the negative of the original function, and our conclusion from that is that this is an odd function. And because it's odd, the symmetry this graph will have is it will be symmetric to the origin. Okay, in this section we're going to be looking at operations with functions. There are several different operations you can do with functions, just like these are similar to operations you do with numbers. So we're thinking of functions as a group of objects, just like numbers are a group of objects, and we want to know, what can we do with this group of objects? So it turns out you can do with functions a lot of the same things that you can do with numbers. So for instance, you can add functions together. So to add functions, we use this notation, f plus g of x. And that is found by taking f of x plus g of x. So if you add those two functions together, f of x plus g of x, you get a new function, which we're labeling as f plus g of x. And the reason we label it that way is so that we can remember how we got that function. So this new function that we've created, we're calling that f plus g of x. And we remember that's the way we got that function. We got that function by taking f of x and adding it to g of x. Or vice versa. If they tell you find f plus g of x, that's a function that you want to find by taking f of x and adding it to g of x. All right. Similarly, we have the following operations. We have subtraction of functions. So if you have this notation, f minus g of x, that function is constructed by taking f of x and subtracting g of x. Multiplication, f times g of x is constructed by taking f of x times g of x. And division, f divided by g of x equals f of x divided by g of x. There's also another operation called composition of functions, which we'll have to talk about next time. So just ignore that for the moment. But for the four that we've just talked about, the big punchline here is not so much that you can do these things with functions, because, why wouldn't you be able to do it? If you want to do it, you could do it. But the big deal here is that when you do these operations with functions, you are guaranteed to have another function. So if I decide to divide two functions, if I take f of x and divide it by g of x, I don't have to vertical line test that result. I don't have to analyze it in any other way. If f is a function and g is a function, then f divided by g will also be guaranteed to be a function. And the same thing with adding, subtracting, and multiplying. If you add two functions together, because the original two things were functions, the result is guaranteed to also be a function. You don't have to do any further analysis to determine that. All right, so let's look at some examples. I'm sorry, we're not ready for examples. Another thing you'll be asked to do in relation to these operations with functions is to determine the domain and range. And so for any of the operations 1 through 3, so maybe what I should have just said there was, for the domain of adding, subtracting, or multiplying functions, you find that by taking the overlap of the domain of the individual functions. So the domain of f plus g is just the overlap of the domain of f and the domain of g. So if we know the domain of the individual functions to begin with, we just look for where those domains overlap each other, and that will be the domain of the new function that we're creating. This is also true for the domain of division. So for number 4, which is the division of functions, we would find the domain by taking the overlap, but we also have to be careful that we don't divide by 0. So we have to make sure we exclude any values that would cause the denominator to be 0, because we're not allowed to divide by 0. And if we're taking f divided by g of x is in the denominator, g of x is not allowed to equal 0. Say that again. X is not allowed to equal anything that would cause g of x to equal 0, because then we would be dividing by 0. So we have to remove any values of x where we might be dividing by 0. That's the only extra requirement if you're dividing functions. Otherwise, it's like the other 3. All right, so let's look at some examples. All right, so the first set of examples, we don't have to even worry about finding the domain. These are just examples of using these functions and plugging a number in and making sure we understand how they work. So this first example, they're asking us to find f plus g of 2. Right. According to the definition, f plus g of 2 is constructed by taking f of 2 plus g of 2. So we can find what this value is equal to by taking f of 2 plus g of 2. And we know how to find these individually, right? How do you find f of 2? You take the function f of x, you plug 2 into it, right? So f of x is equal to x squared minus x, but we're looking for f of 2, so we plug 2 in for x. So f of 2 is equal to 2 squared minus 2. So we plugged in a 2 here for this x. We plugged in a 2 for this x. And 2 squared is equal to 4. 4 minus 2 is equal to 2. And so f of 2 is equal to 2. So what we're going to do is plug that in up here. F of 2, this thing right here, is equal to 2. Right, so replace that. Replace f of 2 with what it's equal to, which is 2. You do the same thing with g of 2. To find g of 2, we start with g of x. We replace x with the number 2. We do that over here as well. And then we simplify. 3 times 2 is 6. 6 plus 2 gives me 8. So g of 2 is equal to 8. So we're going to replace this g of 2 up here with what it's equal to, which is 8. And then we're going to add these two results together, because that's what we're supposed to do. Right? F plus g of 2. I want to take f of 2 and add that to g of 2. So 2 plus 8, which gives me 10. And that's the final answer. All right, let's look at another example. Using the same two functions, let's find f minus g of negative 2. All right, so to find f minus g of negative 2, the definition of what that notation means is to take f of negative 2 and subtract g of negative 2. All right, so f minus g of negative 2 is equal to f of negative 2 minus g of negative 2. It really looks like we're distributing here, but that's a little bit of a dangerous idea, because if you're thinking of this as distributing, you might get the wrong idea that these negative signs could be canceled out, and they can't. They don't get multiplied together. This is not multiplication here, and that's why we really shouldn't think of it as distributing, because distributing is a multiplication process. We are not multiplying here. So just think of this as a definition. The definition of f minus g is to take f of whatever that thing is minus g of whatever that thing is. In this case, it happens to be negative 2. So we'll take f of negative 2 minus g of negative 2. So again, we'll go through the same process we did last time. First, we need to find f of negative 2. How do we find that? We take the function f of x. We replace x with negative 2. Be careful simplifying this, because we're having a negative value here. Negative 2 squared gives me positive 4. And then minus negative 2 gives me positive 2. So we get 4 plus 2, which gives me 6. F of negative 2 is equal to 6. So we're going to replace that. We're going to replace f of negative 2 with 6, because that's what it's equal to. Do the same thing with g. G of x is equal to 3x minus 2, but we're looking for g of negative 2. G of negative 2 is equal to 3 times negative 2 plus 2. So again, replacing x with negative 2. And simplifying, we get 3 times negative 2, which is negative 6. Negative 6 plus 2 gives me negative 4. All right, so we're going to replace g of negative 2 with the number negative 4. And we want to subtract these. So be careful. We're going to subtract negative 4. So we get a double negative there. So maybe we should use parentheses around the negative 4. And when we simplify, minus a negative becomes plus 4, and we get 6 plus 4, which coincidentally, this is not something that normally happens, but we happen to get the same answer we got last time, which is 10. All right. Next example. Let's look at f times g of negative 1. So f times g of negative 1, by definition, that's equal to f of negative 1 times g of negative 1. So same process. To find what this is equal to, first we have to find f of negative 1. So we start with the function f of x. We replace x with negative 1. You simplify, you end up getting 2. So f of negative 1 is equal to 2. So we're going to put that here. Times g of negative 1. Well, so we have to find g of negative 1. Same kind of process. We start with g of x. You replace x with negative 1. You simplify, you end up getting negative 1 there. So g of negative 1 is equal to negative 1. And we're going to multiply these together. So 2 times negative 1, which gives me negative 2. The other thing you'll be asked to do is construct a function without plugging a number in. So we just want to make an equation, not actually get a numerical answer, but make an equation. So for example, this problem here. We want to find f plus g. So let's assume that f of x is equal to square root of x. Now again, you won't be able to assume this on your homework. You'll be given these things on your homework. But so I'm setting f of x equal to square root of x, g of x equal to x minus 2, h of x equal to 1 over x. And we want to find f plus g. This is sort of a lazy way of writing this notation. Really, the full notation should be written as f plus g of x. And by definition, that's equal to f of x plus g of x. And all we have to do, since we're not plugging any numbers in here, all we have to do is replace the function notation with what the functions are actually equal to. So f of x is equal to square root of x, according to this legend over here. So f of x is equal to square root of x, so make that replacement. G of x is equal to x plus 2, so make that replacement. And we want to add these together. And so this becomes our answer. F plus g of x is equal to the square root of x plus x minus 2. So this actually is easier than the problems we were just doing as far as getting that part of the answer. And of course you want to simplify this if you can, but there's no like terms, so we're just going to leave it like this. It's a mess. There's no way to make it look any better. The hard part here is going to be determining the domain of this function. So the domain here, the domain of f plus g, can be found by taking the overlap of the domain of f with the domain of g. So I want to find where these two domains overlap each other. That's the domain of my new function. And so the domain of the square root of x is 0 to infinity. Think of the graph of the square root of x, right? The graph, if you have it memorized, which you're supposed to have it memorized, starts at 0, 0, and it heads off to the right in a parabolic shape. And so how far to the left does it go? It only goes as far as 0. How far to the right? It goes to the right forever. The domain of this function, well, this is a linear equation, and so it goes forever to the left and forever to the right. And so that's the domain, negative infinity to infinity. So to find the domain of my new function, f plus g, I need to find where these two domains are overlapping each other. A good way to do that is to graph the domains on the real number line. So I'm going to graph both of these domains on the real number line, and you get this. The domain of f is from 0 to infinity. That's this blue line right here. The domain of g is in negative infinity to infinity, which is the green line. And where do they overlap each other? They overlap each other right here where I've circled them. And so this is where the overlap is. That overlap occurs from 0 to infinity. And so that's my domain. So it happens to be the same as the domain of f. Again, that's just a coincidence. What you really want to do is find where they're overlapping each other. That's the concrete way of always finding the domain and getting the right answer. We want to multiply two functions together here. We're asked to find g times h. And again, I'm going to define these functions as f of x equals square root of x, g of x equals x minus 2, and h of x equals 1 over x. We want to find g times h, which is a lazy way of saying we want to find g times h of x. So again, they're kind of leaving out some of the details of the notation. And again, that's sort of acceptable, but it's nice to have the full notation there. Before we get started, I just wanted to point out the domains of these functions. F of x has a domain of 0 to infinity. G of x has a domain of negative infinity to infinity. And h of x, being the function 1 over x, has a domain of negative infinity to 0, union 0 to infinity, because what we're doing there is we're leaving out the number 0. X is not allowed to equal 0 in that function, so we're skipping over 0. All right, and we want to find the function g times h, which is g times h of x. So let's go ahead and do that. Right? And the definition of g times h of x is that equals g of x times h of x. And what we're going to do is, just like in the last example, we're going to substitute in place of g of x, the thing that g of x is equal to. And in place of h of x, we're going to plug in what h of x is equal to. And we're just going to swap them out. And again, this is easier than the earlier problems we did because we don't have to plug any numbers in and do any calculations. We're just going to multiply these two expressions together, and it usually isn't much work, because usually there's not much you can do to simplify. So in place of g of x, we're going to plug in x minus 2 because g of x is equal to x minus 2. So in place of g of x, we're going to have x minus 2. For h of x is equal to 1 over x. And so in place of h of x, we're going to plug in 1 over x. And what we want to do with these two functions is we want to multiply them together. And we are multiplying it to a fraction, right? X minus 2 is getting multiplied to a fraction, so be careful how you think about that. Think of x minus 2 as a fraction. Think of it as being over 1. And when you multiply these together, you end up getting x minus 2 over x. All right, and that's all you can do. There's nothing else you can do to simplify this. So I guess you could write it in a slightly different way, but you might as well just leave it this way. So you get g times h of x equals x minus 2 over x. So again, that's really not too hard to do. You just slap the two functions together and you're done. I kind of think the hard part is determining the domain of this function. So we need to determine what is the domain of this new function that we've just created. And the rule is the domain of the new function will be the overlap of the domain of the original functions. So I need to take, in this case, g and h. Let's find where these two domains overlap each other. That will be the domain of g times h of x. And so a good way to find where they're overlapping each other is, again, to draw them both on the same real number line. So I guess I forgot to label this one here, but the domain of G is all real numbers, so it's this green line here. It covers everything. The domain of H is everything except for 0. So we use an open circle to skip over the number 0. So we shade in everywhere else except for the number 0. Where do these overlap each other? They overlap each other almost everywhere except at the number 0. So they overlap everywhere to the left of 0. That's this interval right here, negative infinity to 0. And they overlap everywhere to the right of 0, which is this interval here, 0 to infinity. And we union those together. And so again, it coincidentally turns out to be the same domain as h of x to begin with. But again, you want to find where they're overlapping each other. That's the domain of the new function that you've just created. So the new function is x minus 2 over x, and its domain would be negative infinity to 0, union 0 to infinity. Right. I want to look at one more example at this time anyways. So let's find g divided by f. And so the two relevant functions here are going to be f of x equals the square root of x, and g of x equals x minus 2. We want to find g divided by x. Again, that's a lazy way of saying we're looking for g over f of x. So that's the rest of the function notation there. A little bit later on, this will become relevant. The domain of f is 0 to infinity again, and the domain of g is negative infinity to infinity. All right, so g over f of x, by definition, is equal to g of x over f of x. And I guess I got a little bit ahead of myself here. So what we're going to do is replace. We're going to replace g of x with x minus 2, because that's what g of x is equal to. And we're going to replace f of x with the square root of x. And so it'll look like this. And again, there's really not much we can do here to simplify. You could rationalize the denominator, but for the purposes of this exercise, it's okay to just leave the square root in the denominator. Right? And so that's our final answer. That's what g over f is equal to. Now let's find the domain of this new function we've just created. To do that, we want to find the overlap of the domains of the original two functions. But this is something we've already done. We did f plus g of x earlier, and in that case, we found the overlap of the domains of f and g, and they're going to overlap in the same way here. So even though we're doing something different with the functions this time, the domains are going to overlap in exactly the same way. And what we found earlier is that they overlap from 0 to infinity. And so that's going to be the domain of this new function we've created. Almost, right? There's one little extra detail we have to be careful about. So if you recall at the beginning of this section, when I talked about finding the domains of these things, the domain of the division of functions has an extra precaution that we have to take, in that we don't want to divide by 0. So f of x by itself, it's okay for f of x to equal 0. You can plug in 0 for x here. You get the square root of 0, which is 0, and that's okay when f of x is by itself. But when f of x is the denominator of a fraction, that's not okay anymore. You can't have 0 in the denominator, so it's not okay for f of x to equal 0 at this point. But the domains don't reflect that yet. And so when would f of x equal 0? It's equal to 0 when I plug in 0 for x. And I have to take that out of the domain because that's no longer okay to do. And so here 0 is being included, right? The brackets includes the 0, but technically in this new function we've created, 0 is no longer okay, so we need to remove 0 from this domain. Right? So here it's not okay for x to equal 0 in this denominator, which means we're going to change this bracket to a parentheses. And now we've left 0 out as well. And so that's the domain of this new function we've just created. The new domain will be 0 to infinity, not including 0. All right, so that's the domain.